Good morning. I'm Owen He from Maker AI. Because the authors cannot attend the conference for visa problems, I'm presenting on their behalf. The credit of the amazing work goes to the team from CAI Lab, National University of Singapore, and Singapore Management University. So as we all know, DeepSeek R1 was the first open-weight model demonstrated strong reasoning capabilities that matches OpenAI O1 model. What's remarkable was that R1-Zero achieved reasoning ability using only reinforcement learning base models without any supervised fine-tuning. An interesting observation was that the double increase phenomenon, as the model's performance improved, its response length was also becoming longer. The left plot here shows that R1-Zero accuracy on a task increases over time, and on the right plot, it shows that the average length per response also increased during training. A common belief that explains this phenomenon is that in order to get higher rewards, the model has to think more. Therefore, a long chain of thought naturally emerges. In this way, the model will be able to do something more sophisticated like self-verification, and this will give it a higher average reward. But another possible but more subtle confounding factor is that maybe the GRPO algorithm that R1 used actually leads to biased policy gradients that affect response length over time. And this was the problem studied in this paper. To understand the problem, we need to revisit policy gradient for LLMs. At the very high level, our objective is to optimize the reward, expected reward over the questions queue and the output tokens generated by the model pi theta. If we look at the policy gradient, which can be written in the second form here using the log derivative trick, you can further factorize the log probability into a sum of log probability of each token. And to further reduce variance, you can subtract a baseline from the reward, and this will not affect the mean expected value. This final form already looks very similar to the formula used in the GRPO training objective function, but they're not exactly the same because there are two extra terms in the GRPO formula. One is the length normalization. The other one is the standard deviation normalization. Now, because of these two extra terms, the GRPO algorithm actually leads to biased policy gradients. The length normalization term leads to a response level length bias that makes the correct responses shorter and incorrect responses longer. The reason is that when the response is correct, the reward is usually positive. So to maximize the objective function, the gradient will want to make the denominator smaller, therefore reducing the length of the response. And when the response is incorrect, the reward is usually negative. So to maximize the objective, you will try to increase the denominator and making the output longer. And the standard deviation normalization will lead to a question level difficulty bias, because for questions that are too easy or too hard, the rewards are either all very high or all very low, so this will give a low variance of the rewards, and therefore the corresponding gradient for these questions will be upweighted. Now, since the length normalization has different effects on the correct responses and incorrect responses, one might say that, well, maybe they will cancel each other out. It's not necessarily true that the response length will grow over time. But the problem is that this effect is actually asymmetric, because for correct responses, you need a certain length of reasoning to remain correct. So if you keep shortening the answer, at some point, it won't be correct anymore. Whereas for the wrong responses, you can keep increasing it, and the answer will still be incorrect. So the overall dominant effect of this bias is actually increasing the response length. Now, with these biases understood, the authors proposed to correct GRPO by simply removing these normalizations, and their modification is called Dr. GRPO in their paper. Compared to the original GRPO, Dr. GRPO has higher token efficiency. In this plot, we can see that over training progress, the average output length is much shorter, and it achieves a higher average reward. And in these three plots, we can see that the reward for both Dr. GRPO and GRPO are almost the same. And for the correct responses, they also have similar lengths. However, for the incorrect responses, Dr. GRPO has significantly lower lengths of the response. There's another work that also addresses the double increase problem called DAPO. Instead of dividing the terms by the length of each response, in DAPO, they divide these terms by the sum of all the responses in a group. Now, this will have less bias because each response now share the same normalizer in the same group. But however, this sum of responses will depend on the question, so this actually introduces a question level bias. On the other hand, Dr. GRPO is unbiased because it's using a constant as the normalizer, and this constant does not depend on the question or the individual response. And it can also be regarded as the horizon in the finite horizon Markov decision process. The authors also found out that most of the open source implementation of RL framework for LLMs actually implicitly introduce this length bias because they're using mean reduction in the loss computation instead of sum. And when you use mean reduction, it's effectively dividing the loss by sequence length. To fix this problem, one can simply replace the mean by sum in the policy gradient computation. To zoom out, if we look at the R1-Zero paradigm from very high level, there are two, it's basically applying RL on pre-trained base models. So there are two components, the RL component and the base model component. And so far, the paper has focused on the bias in GRPO, which is the RL component. As a second contribution of the paper, the authors look at the base model component, and they pose the question, what properties should the base model have to be successful in this RL training paradigm? In particular, they observed that for many works that try to replicate R1-Zero, it's often the case that the Quinn model would work better than other open weights models, say Llama. So for instance, here in this plot, given the same number of RL steps, the Quinn model can converge to much faster and to a higher value of score in the end. So this leads to the author to pose the question, what makes Quinn so special? Why is it a better base model for RL training? To answer this question, the authors took the Quinn base model and applied 3 different templates to turn the original base model into a QA model. Because the original base model are usually pre-trained to be a sentence completion model, and for QA models, you want to generate answer conditional on questions. So the 3 templates they used are R1 template, which prompt the model to generate thinking tokens wrapped by the think tags, and the answer wrapped by the answer tags. And the second template is the Quinn math template, where they use the delimiters from Quinn models, and they prompt the model to reason step by step in a chain of thought way. And as a control group, the authors also use no template, where you just give the question to the model and prompt the model to generate the answer. To their surprise, the best initial performance of the model is actually achieved when there's no template. It seems that the RL, if we look at the other 2 templates, it seems that the RL actually achieved a much higher improvement with R1 template and Quinn math template. But if we look at the initial performance, it seems that the improvement actually comes from restoring the ability that the model originally have, but it was just initially destroyed by the templates. And this phenomenon was not true for other models, other open weight models the authors compared to. So one hypothesis the author had was that maybe Quinn was already pre-trained on math QA data so that it doesn't really need a template to generate answers given questions. So their hypothesis is equivalent to maybe if you use domain-specific mid-training, this would improve the RL ceiling performance. To verify this hypothesis, they took a llama model and added mid-training to it. The blue curve here is the original llama 3.2 3B model. And on top of that, they fine-tuned it on fine math to get the base model for the green curve here. And then on top of the green base model, they fine-tuned on Numina QA model to get the base model for the red curve here. Starting from these three base models, the authors performed Dr. GRPO training. And as we can see that with more mid-trainings, the llama model has significantly better post-RL performance. So this seems to show that if you add domain-specific mid-training, you can improve RL seeding performance. To conclude, the authors demystified a powerful paradigm for training reasoning models, which is the RL-VR from base models. They fixed the biases of GRPO to make the GRPO unbiased and more efficient. They also showed that strong task prior of base models is a key property for RL trainability. Now, because I'm not an author, I will not take questions. If you have any questions for the author, please take a photo of the QR code, which will link to their contact info. Thank you very much.